Okay, in this chapter we're going to cover the material from chapter 3. This chapter is kind of long, so I divided it into 2 videos. Okay, so we're going to cover the ordinary least squares model. Ordinary least squares, called OLS, is a popular method for estimating parameters of a statistical model. So for example, assume that earnings can be represented as an additive linear function of some regressors. Usual regressors we might use are things like years of education, years of labor market experience, gender, whatever we think affects earnings. And we wish to estimate how each of the regressors affects earnings. Okay, the estimated OLS coefficient, beta 1, beta 2, up through beta k, will give us the change in y I induced by a change in xi, for each of these x's. So if this is the model, then the derivative, which is the change in y induced by a change in x, gives you a measure of the effect of a 1 unit increase in xi. Okay, so for example, if one of the x's is education, that would be the effect of 1 year increase in education on earnings. If y is measured in logs, then that actually corresponds to the percent change in y from a 1 unit increase in x. Okay, so in this model, notice we have an error term here. How do we interpret that error term? Well, there are multiple interpretations. One is that the dependent variable y could be measured with error, and that could lead to measurement error. Okay, so that just means there's some factors, that affect y, some reporting errors, say, and we don't have those factors in our data, so that's why we'd say it's an unobservable factor. Epsilon is unobserved. Or it could represent the effect of omitted x's. So suppose you have some omitted determinants of earnings, and usually to apply OLS, we have to assume that the omitted factors are independent of the included factors. Okay. Later on, we'll consider when some of the omitted factors are not independent, what happens. Okay, so to begin with, when we're looking at the OLS model, we're going to assume that the x variables are non-stochastic. That means that we can treat the x's as if they were just constants, and that the only source of random variation in y is going to be the residuals. So why do we make this assumption? Well, basically, this just makes some of the results simpler to derive. This is like the original way the OLS model was analyzed. And then later, we're going to consider a more modern approach where we also allow the x's to be random. But just for simplicity of, presentation and understanding, we're going to at first assume that the x's are constant. So in chapter 9, we'll relax this assumption. Okay, so the OLS model makes certain assumptions on the error term, and these assumptions are considered part of the statement of the model. So the model would be incomplete without including these assumptions. And the reason is you really need these assumptions to pin down the beta. Okay, so these assumptions are often called identifying assumptions. Okay, so first we'll make an assumption that the error term has mean 0. Okay, then we'll make an assumption that the variances are the same across different observations. This means that the error terms are homoscedastic. Okay, so if epsilon has mean 0, then E of epsilon I squared is the variance of epsilon. Okay, and lastly, we'll make an assumption that the error terms across different observations, I and j, have 0 covariance. Okay, so the covariance here is equal to this expectation minus these two terms. Each of these terms is 0, so the covariance is just E of epsilon I, epsilon j, and we'll assume that's 0. So the OLS estimator is going to choose the coefficients to minimize the sum of the squared residuals. Okay, so let's consider the OLS estimator in a very simple case. And the simple case is going to be where we just regress y on a constant term. So the only regressor is xi1, which equals 1 for everybody. Okay, the OLS estimator minimizes the sum of squared errors. Okay, and this is a constant term, so this is the problem it's solving. So to solve for the beta, you would take the derivative with respect to beta. All right, set that equal to 0. And you see that beta hat, so this is the OLS estimator, is the mean of the y's. Okay, so beta 1 hat is the sample average of the y values. So we distinguish a true parameter from the estimated parameter by putting a hat over it. Okay, the true parameter is unknown. Okay, and the estimated parameter is what we're trying to form to get a good guess about what the true parameter is. Okay. Okay, the residuals from this regression are called the fitted residuals. And that's when we use here beta hat. And we denote that epsilon I hat. The true residuals, on the other hand, we would write without the hat. And see here we put the actual beta. So the true residuals we don't know because we don't know the true beta. Okay, but the epsilon hats we do know, because we have the beta hat from solving the OLS problem and we can construct epsilon hat. All right, so let's consider a little bit of a richer model where we now introduce some categorical variables. Okay, so we're going to have two regressors. The first regressor is just a constant term. And the second regressor is an indicator that equals 1 if person I is female. So I'm assuming these observations correspond to different people. And it equals 0 if person I is male. So the OLS estimator is solving this problem here. So now note that we have two unknowns, and we would have to take the derivative with respect to each of these, right? And then solve for them to get beta 1 hat, beta 2 hat. Okay, so I divided this up into a little bit of a simpler problem so that you can see maybe a little bit more clearly what the beta 1 hat and the beta 2 hat are. Okay, so the summation is over all individuals, so we can divide up the summation into males and females. Okay, for males, xi2 is 0 for all males because it's only 1 if female. Okay, so for males, they just have beta 1, and for females, they have this. Okay. Now we could call this just gamma, this term here. And you can see that beta 1 hat is going to correspond to the mean of for the males. And then this gamma hat is going to correspond to the mean for the females. Okay. And this implies that beta 2 hat is going to be the difference in the mean for females minus the mean for the males. Okay. So if you have this model where we have an intercept term and then an indicator for a female, the intercept term is going to give you the mean for males, and then the indicator, the mean for females is going to be beta 1 hat plus beta 2 hat. So beta 2 hat will give you the difference in the means between the female average and the male average. Okay, just to make it concrete, like suppose women, the average was 12,000 and for men it was 10,000. Then beta 1 hat would equal 10,000 and beta 2 hat would equal 2,000 because it's the difference between the female average minus the male average. Okay, so if you obtain these coefficients, let's say from estimating that regression, these estimates imply that males make on average 30,000 and females on average 27,000. because it's 30,000 minus 3,000. Because this xi2 is one only if female. Okay, so we can extend this model to add more categorical variables. So categorical variables occur quite often in economic application because lots of things are categorical. And there's actually a pretty big literature in labor economics that tries to estimate the effect of unions on wages. Okay, so here in this regression, we have a female effect, a union effect, and then a female interacted with the union. And this is allowing for the union effect. So if unions increase wages, so this would be like the union wage premium, to differ for females and males. Okay, so we can write it this way. So x1i here would be just an intercept, because everybody gets this. And then x2i would be an indicator of female. x3i, or here I see I swapped i3 and 3i, but this should be just i3 is okay. So xi3 is a union indicator. And then this variable here would be 1 only if both female and in a union. So these terms are called main effects, and this is an interaction effect. Okay, so note that there are 4 possible categories: male non-union, female non-union, male union, and female union. Okay, and these coefficients, so if you're male non-union, the only coefficient you get is beta 1. If you're female non-union, you will get beta 1 plus beta 2. If you're male union, you'll get beta 1 plus beta 3. And if you're female union, you get beta 1 plus beta 2 plus beta 3 plus beta 4. Okay, and so we can actually calculate these betas if we know the means for each of these categories. So for example, suppose the male non-union, if that mean was 20,000, then beta 1 equals 20,000. Okay, and if the female non-union mean is 18,000, that means that beta 2 is minus 2,000. Okay, because beta 1 plus beta 2 have to add up to 20,000. So in this case, you have 4 different means, and from those 4 means, you can calculate what all of these betas are. Okay, and in this type of model, there are 4 means, there are 4 parameters. We call this a saturated model. Okay, because note that, we have 4 different categories, and then we have 4 different parameters, which basically capture the means for all these categories. Of course, you could run the regression omitting this interaction effect if you wanted to, but that would be imposing a restriction on the model. So you cannot, actually in that case, you'll lose the interpretation of means. All right, so it's not a good idea. It's generally a better idea to write down a model that's fully saturated if you're able to. Of course, if you have, 3 or 4 different categorical variables, then it kind of gets to be complicated to put all possible interactions in there. So if you have too many categories, then you may have to have a more restricted model. But if you just have 2 categories, it's pretty easy to estimate the fully saturated model. And the nice thing about the fully saturated model is you can interpret the regression coefficients as means for the different categories. Okay, and there's always different ways you could write it. Okay, but there would be a mapping between the coefficients. So for example, I could write it in this way, where like di1 equals 1 if male and non-union. di2 equals 1 if male and union. Okay, so in this model, there's no intercept. We just specify dummy variables dummy variable is the same as an indicator variable for each of the categories. Okay, and so in that case, alpha 1 is going to be the mean for male non-union. So if that was 20,000, this would be the mean for that category. Okay, so you see how this is a different way of writing the model. And the coefficients, you'll get different coefficients because it's set up differently, but there's a mapping between the alphas and the betas. Okay, and actually the fitted residuals from these two models, like either the one with the betas or the one with the alphas, would be exactly the same. Okay, all right, so this concludes just the introduction to the OLS model and categorical variables. Okay, in the next video, we're going to look at how you write this model in matrix notation, and then we're going to solve for the OLS estimator.